So today we're going to see the 5G network slicing. All we need to know regarding the 5G network slicing is how the slicing is being done in the 5G network and how it works. Why do we go for network slicing? So starting from the basics, we'll go through with the referred examples. Then we'll deep dive into slicing concepts, how it is getting implemented in 5G communication networks, and then we'll move on to RAN slicing. So starting off with introduction part, let's understand what is network slicing before we go into deep with network slicing concepts. So this slide basically provides a visual explanation of network slicing, a core feature of 5G networks that enables multiple virtual networks to run on a shared physical infrastructure. So the key elements here are we have two elements, that is UE1 and UE2, which require different network services. Basically, UE1 wants to connect with an IoT device, and UE2 wants to connect with internet, basic internet. So here, the radio access network plays as a shared wireless network part, which connects the user devices to the core network. So each colored area, that is the blue colored area, is one slice, and the green colored area with purple one is another slice, and green color is another slice. It represents different slices, virtualized and isolated end-to-end network paths tailored for specific use cases or service types. So here, starting with the first slice, that is blue color. So the user equipment 2 wants to access internet. So here the dedicated user equipment 2 leads to standard internet services. So then it's come on to the slice 2 where it handles IoT device 2 optimized for your specific requirements, that is green slice. So here in this green slice also we have two different types of services provided. One is IoT 1 and another one is IoT 2. So here we do have common elements like access and mobility function, which can be shared across the two different slices, slice 2 and 3, that is slice for IoT 1 and IoT 2. Each slice has its own set of core network functions working behind, such as session management function, policy control function, and user plane function to meet their slice needs. Here, the dashed lines represent the non-access stratum signaling control path connections from the user equipment through RAN to the core network. The solid lines indicates the data traffic routes from user equipment to their intended services or external networks. So usually here behind the scene, we have some specific identities like unified data management, network slice selection function, network repository function, working on with the slices for critical management that supports all network slices by managing the user data, selecting the network slices, and storing the network function information in a specific area. So, for example, IoT devices can use dedicated slices, ensuring their connectivity and performance is very much met in this particular concept network slicing. So, basically, this diagram demonstrates how multiple isolated virtual networks are created on a single physical infrastructure, each optimized for different types of users or services, enabling efficient, flexible, and scalable 5G network deployments. Next, moving on to our next slide, where this slide illustrates the historical challenge faced by the network operators in delivering the diverse services. So it actually has grown as a variety of user devices known as user equipments, and different types of user equipments are there. Where this particular image shows a range of devices such as smartphones, smartwatches, IoT appliances, and wearable devices, and so on. These represents the increasing diversity of equipments connecting to the specific mobile networks. So the orange box actually, you can see that the have very different network requirements. Each and every device will have the different network requirements, which go far beyond what could be managed by traditional quality of service differentiation. For example, wearables may need ultra low power and simple messaging, while smartphone needs high bandwidth and fast connectivity. So here we have two colored lines that is from cell tower to reaching different parts of the image that is starting from red color. So one core network is optimized for smartphones, supporting like high-speed data, voice, and multimedia. And another is actually for optimized IoT devices tailored for massive connectivity, energy efficiency, and sometimes lower latency or reliability needs. So the slide highlights how proliferation of device types and their widely differing service requirements created complexity for the operators who needed dedicated network cores and could not meet all needs using only basic QoS flows. This sets the stage for innovations like network slicing in modern 5G. So here, in modern telecommunication networks, specifically, how a single operator network can concurrently serve different types of customers and services through different dedicated virtualized slices. The network slices, each row in the central box actually will go through one by one. So each box, the central box describes the distinct network slices, which is virtual network running on a shared physical infrastructure. So, for example, the smartphone slice one. This for an operator, direct subscriber, example, a customer or of a main telecom brand can use this particular slice. Next is for the smart slice 2, the smartphone slice 2 is for virtual operator subscriber. That is customers who use a mobile virtual network operator who can use this particular slice. Next is the vehicle service slices, is like dedicated to connected car services for a car manufacturer, possibly supporting functions like telematics, infotainment, and autonomous driving, and so on. Next comes the non-public network slice, which is used for specialized private networks, such as a factory dedicated communication needs, basically a non-public network. So the lower section, there is the behind section, portrays that these slices span the entire part from the user equipment, like smartphone or car systems or anything it could be, an end equipment, through the radio access network into the core network and finally reaching the data network. This means that each slice is an end-to-end encompasses all necessary components for a specific service without any interruption. So when we choose the correct slice, when the network slice has been correctly chosen for a specific service, we'll have an end-to-end connection where we'll not have any interruptions or interference or anything, and the performance of the network goes very high. So finally, the network slicing allows the operator to partition the networks virtually so they can securely, efficiently, and flexibly address the very different needs of the consumer, enterprise, and industry use cases all at once over the same underlying infrastructure. So the next goes on with the standardization timeline. So the release 15 actually introduced the foundational concept of network slicing, enabling multiple virtual networks to coexist on a shared physical infrastructure in 5G network. Going ahead, release 16 brought enhanced network slicing, building on the initial network slicing capabilities by providing improved features and support for advanced use cases. And in addition, release 17, it focuses on the further enhancements named as ENSPH2 or RAN slicing. And this RAN slicing improves how the RAN enables and radio access network enables and manages the network slices, not introducing to a whole new concept like slicing concept. So basically, this slide outlines how a network slicing capabilities are introduced progressively by 3GPP from release 15 to release 17. Next, we'll go on for in detail what is network slicing. So here in this slide, we can see that there are up to 8 slices actually. 8 different slices can be supported with each represented different colored path, and each slice is a virtualized end-to-end logical network that can be tailored for a specific application or a service requirement. The slices run over the same physical infrastructure but are functionally isolated from each other. So each slice utilizes its own set of core network functions, that it has specific network functions like access and mobility function, session management function, user plane function, and policy control function. So some functions like NSSF, that is network slice selection function, network repository function are common for all slices for a given user equipment. These are used specifically for discovering and selecting the appropriate slices. So connections originate from the user devices, pass through the RAN, and are separated into slices according to the service or user requirements. So each slice can connect to a different data network like DN1, DN2, DN3, DN4, section 4, and multiple PDUs, protocol data units. Sessions are possible for per slice. So the here, in for a better understanding, the solid lines actually represent the data plane, that is user data traffic, and the dotted lines represent the control plane, that is signaling and session management functions. So slices may be implemented via scheduling L1, L2 configurations and bandwidth paths also through exact details detailing paths. So this gives a simplified view on how multiple logically separated network slices are provisioned in 5G network, each with dedicated network functions providing tailored connectivity and services to meet the diverse application needs, all while sharing the same physical infrastructure. Um, this Here we can see the examples of network slices within a 5G network, how each is tailored to the requirements of various service categories across the operator infrastructure. So here, starting from the left to understand what it is. So we have a critical IoT, that is ultra reliable, low latency communication. This means very high availability and very low latency. For example, it could be used in industrial automation, mission critical applications, and so on. Next is enterprise industrial IoT, requires high availability and low latency, which is used in smart factories and enterprise systems. Next is enhanced mobile broadband, designed for wide area coverage and general internet operator service like streaming, web access, general cellular users, and so on. Last one is massive IoT, which prioritizes low cost, low energy consumption, and can support a massive number of devices. For example, we can consider sensors, meters, actuators, and so on. So the next coming part of is the middle part, where we have the each part of the example has been explained, and then now we move on how it is getting implemented in our 5G. So the custom resource allocation is done where each slice uses a different set of network functions and resources across the key infrastructure layers for specific example. So for example, when we go for critical IoT, we have a criteria that we need very high availability of the network and the latency should be very, very minimum. In that case, we have three user plane functions working in parallel along with the control plane functions and the PCF. So when the even the network slices choose the number of components or the components according to the severity of the service or according to the requirements of the service, where each particular slice is customized according to the service needed by the customer. So basically, this is how the 5G enables customization, concurrent network slices for different service categories, starting from critical IoT to broadband to massive connectivity, each with its own network resources and functions, delivering tailored performance and capabilities over a single shared 5G infrastructure. So now let's go on in deep, like how a network slice is getting identified. That is, we have to choose a network slice for specific services so that the selection of network slice makes the network more efficient. So the challenges of identifying a network slices in 5G are very high. So basically, a network slicing enables a mobile network to be logically divided into multiple virtual networks on top of the shared physical infrastructure. So each slice is optimized for specific service types, like as we saw in the previous slide, starting from critical IoT to mobile broadband and low latency services in massive IoT. So here the mobile device wants to use a network slice but may not know which slice exists actually. So the base station here may not respond for informatively if a device requests a non-existent or unknown slice. So it is like the user equipment is telling, I want to use a slice, but which slice do you need? What kind of service you wanted me to offer? That data is missing over here. So the network cannot inform the device properly. So again, it gives a request or it gives a question that what kind of slice you need. So the user equipment again communicates with the tower stating that I want to use a slice with number three. But the slice number three is actually it is not available in the specific tower. So again, the communication goes such that it doesn't have. So this shows that without clear slice identification, devices and users cannot easily select the slice best that is best suited for their needs. So the applications requiring specific attributes may not be able to request the correct slice unless the precise mapping and discovery mechanisms are in place. Actually, here the unresolved area in the network slicing is how to advertise and map available slices and their associated services to the devices in an automated way or standardized way. So here, this is how the devices discover and select from multiple service-specific network slices. When there is no current or standardization method for current slice identification or slice mapping. So solving this, we go for potential flexible service awareness of 5G networks. And this goes in where we go for network slice selection assistance information. So it means actually for uniquely identifying and selecting network slices within a public LAN mobile network, which is necessary in 5G architecture due to the coexistence of multiple virtualized networks over shared physical infrastructure. So the key terms used here, you can see that NSSAI, that is Network Slice Selection Assistance Information, for a device or for a service. So yes, NSSAI is nothing but the fundamental unit representing information for a single network. Each slice, each SNSSAI helps the network and device agree on virtual slice to use for a typical connection. So this NSSAI enables both the network and device to identify and use the correct slice matching the user or the service requirements. And the NSSAI is typically a collection of list of SNSSAIs. The maximum number that may be listed depends upon the network specifications. So here, under SNSSA, that is Single Network Slice Selection Assistance Information, we have two identities called as SST, SD. SST means Slice Service Type, SD means Slice Differentiator. So SST dictates what kind of network experience or service guarantees are provided, and SD allows finer segmentation, for example, separating premium from standard users, even when both use the same basic network service. So why this is important? Why we have to go for an assistance information regarding the network slice information is this allows the operator to efficiently allocate resources, assure quality of service, and customize the network for varied use cases over the same physical infrastructure. The devices and applications get the performance, latency, security, or reliability they need mapped to the appropriate slices via the SNSS so basically, this is how the SNSSAI enables precise identification differentiation of network slices to support diverse services, users, and application needs in the modern mobile network. Next, how the SST values are being categorized and how it is getting selected. So basically, as we saw in the previous slide, SST service slice service type. It is a mandatory identifier used to classify the network slices based on their intended use or service features. And SD is nothing but it's optional slice differentiator used for finer differentiation within the same slice or service type. So here we have two types of SST values. That is one is standardized values defined by global standards ensure slices are interoperable across networks and vendors where we don't have the service differentiator. Another one is non-standardized values where we have it can be SST alone or SST with SD, the service differentiator, defined by the network operator themselves and used only within the operator's own network not meant for general cross network operability. So here we can see that we have the slice type, SST value, and the characteristics. So basically, for 5G enhanced mobile net broadband service, it is high speed data streaming. We use SST value 1. And for ultra reliable low latency communications, we use 2. For massive IoT, connecting large number of IoT devices, we use 3. For vehicle to everything services, we use 4. For high performance machine type communication, we use 5. 6 to 127 is reserved for future user specification, and 128 to 255 is operator specific for operator defined internal users only. So it means that it allow operator specific allowing custom network sizes tailored to operate or enterprise needs, useful for private or specialized networks. So here, why we have to go in much concentrated with SST value is it enables precise matching of network resources to service type, supports multiple concurrent services on same infrastructure, facilitates automation and flexibility in network management, supporting new applications like autonomous vehicles, smart factories, personalized broadband, and so on. So SST values are the backbone of network slice identification and differentiation in 5G, enabling operators to design and deliver a wide variety of network services, each optimally supported by the network according to the technical and business needs of the user and application. Next, we are moving on to the relationship between the network slices, video sessions, and data network names in a 5G network for a single user device. So we're considering only single user device, which is user equipment 1 UE. So a logical end-to-end partition of 5G network tailored for specific service requirement or customer needs is shown here. Each slice acts as a virtual network running on a shared infrastructure. So here, the PDU session represents a single IP data session carrying the user data. Each PDU session is anchored to a network slice and connects to a specific data network name. The destination data network for user traffic is nothing but it could be a particular DNN1, DNN2, DNN3, and so on. So each user equipment can connect to multiple slices up to 8 and multiple PDU sessions up to 15. Inside each slice, user equipment can establish one or more PDU sessions, each point to a different DNN. So here in this slide, we can see the slide 1 serves PDU session A, which connects to DNN. Slides 2 runs on PDU session B and C, and PDU session C to DNN2. And slice 3 actually it handles the PDU session D, that is with respect to DNN3. So this configuration shows the flexibility. The sessions can be mapped across slices and DNNs based on the user or service demands. The structural flexibility of 5G networks is shown here, allowing a user device to maintain multiple simultaneous isolated data connections across various network slices and data networks, providing tailored connectivity and services for modern applications.